Hello everyone. We are starting today with a new concept called thermochemistry. Now, in thermochemistry, what's basically is done, we are dealing with enthalpy changes, right? So, thermochemistry, the definition is the measurement and interpretation of enthalpy changes due to chemical reactions, formation of solutions, and in change of states. So, basically in thermochemistry, we are trying to deal with the changes in the enthalpy when you're having any reaction. So, if you are having any kind of reaction, okay, say two things are combining to give a third thing. So, two reactants are combining to give a product, or you're dissolving something in a liquid, or you're burning something. So, all these kind of reactions in themselves will have some kind of enthalpy changes. So, we are trying to understand enthalpy changes in all these different kinds of reactions, right? So, this is the realm of thermochemistry. So, basically this is related to enthalpy changes. Now, if you remember from before, what was enthalpy? So, enthalpy was defined as E plus PV, right? So, just to keep in mind what we are dealing with in here. Previously, we have defined this quantity, H is called enthalpy, and in the chapter related to the specific heat capacity, we also came up with this term Cp, which has a relationship of something like this. So, these two equations were previously introduced in our course. So, we will be using these two as a starting point for this equation. Now, we are dividing thermochemistry in basically a few different sections. Now, section 1 will be dealing with basic concepts and definitions, delta H versus delta E, what's the difference. We'll be again revising some concepts about exothermic and endothermic reactions. We'll be dealing with thermochemical laws given by Lavoisier and Laplace, Hess and Kirchhoff. So, we'll have Hess's law, Kirchhoff's law, etc. And then we'll be introducing the concept of elemental reference states. So, this will become very important. We'll be defining baselines for calculating H, right? Because enthalpy is a quantity which, if you want to calculate the absolute amount of H, it's not possible. So, it's like the pressure or potential. So, in physics, you must have heard about the word potential, right? Whenever you find a potential, like the potential energy, so you cannot find out the exact potential energy of a system. You always calculate the potential energy with respect to a baseline, with respect to a reference. So, in here, we'll be introducing the concept of elemental reference states to actually find out enthalpy, because the absolute value of enthalpy cannot be calculated. So, you always have to find a reference. So, we'll be defining the concept of elemental reference states. Then we'll be introducing the concept of enthalpies of solution and dilution. So, if you dissolve, say, a base like a potassium hydroxide, if you're dissolving potassium hydroxide in water, then you release some kind of energy, right? So, we'll be trying to see how we define those kind of energies and what's the energy exchange when you're dissolving certain things in solutions. So, those things will be introduced, and then we'll have enthalpies of ionic reactions in aqueous solutions. So, that will be more or less a section 1 of this thermochemistry. Section 2 we'll touch upon the applications of thermochemistry. Like, we'll be dealing with how we can apply the laws and the concepts that we learn in thermochemistry into finding out the bond dissociation energies or the ionization potentials, ionization enthalpy, ionization potentials, and electron affinities. So, the second part will be dealing with more of the application aspect of thermochemistry. But the first aspect that we are starting with is the basics concept. And to start with the basics, we are just trying to find out what's the difference between delta H and delta E, right? Enthalpy change, the delta H, and the internal energy changes, delta E, okay? So, previously we defined H at a constant pressure. So enthalpy was defined at a constant pressure. Why was it defined as a constant pressure? Because most of the reactions that we have on the Earth's surface are generally isobaric, generally constant pressure processes, whatever it's happening. So like, for example, if you are driving a car, that is happening at a constant pressure. The exhausts of your car engine are working. Gases from inside the exhaust are coming out. So that is a constant pressure process. Okay, you're drinking caffeinated drinks, like that is a constant pressure process. Like you're opening up the can. So those things, like most of the things in our atmosphere are on the surface of Earth are constant pressure processes. So we do not observe a lot of like pressure changes in our system. Most of the pressure changes are in the order of 1 to 3% changes, which is like 1 to 30 millibars range, which is not a lot for most of the ambient conditions. It might be a little more when you have extreme weather conditions, but for most practical purposes, we will think of the superficial terrestrial processes as constant pressure processes, and that is why the concept of enthalpy, which is defined at a constant pressure, becomes important. Okay, so we also remember that the heat exchange that happens at a constant pressure is basically the delta H, right? The enthalpy change, the final minus initial. Okay, now there is this concept of delta H. Now delta H can be defined for, say you are having a reaction in which you are going from reactants to products, right? So the delta H of this reaction will be defined as the summation of the products. The VI, I'll be defining what VI means in just a moment. Okay, so VI in here is the stoichiometric coefficients of the various products in that reaction, and HI is the enthalpy of each compound. For example, like if you have a reaction which goes from like a very generalized reaction, a very generalized reaction like this, so the delta H will be the sum of the, so these are the products, so you'll have C times the H of C plus D times the H of D minus A times the H of A plus B times the H of B. Okay, so this is the normal, this is how you'll calculate the delta H. So let's name this equation, number this equation as equation number 27 from before. So we are going into a continuation of those of the numbering of the equations. Okay, in a similar fashion like that we did for the delta H, we can also write for the same reaction, we can also write the delta E, right? So it's exactly the same thing. We're just writing the delta E. So delta E then becomes summation of the VI, the stoichiometric coefficients of the products minus summation of the stoichiometric coefficients of the reactants. Okay, And this becomes equation 28. Okay. Now we see that the delta G, the delta H and the delta E are two different things. Now there is a difference between delta H and delta E. Why? Because there is an inherent difference between the two as it is defined. So now let's calculate the difference. Since delta H and delta E are two different things, let's try to bring them into one equation and try to find out what that actually comes out mathematically. So we'll start with H being E plus PV. We would like to find out the difference between delta H and delta E. So let's do the differentiation on both sides. Okay. This becomes delta H, this becomes delta E. Now this differentiation will turn out to be something like this. This is basic calculus, I hope you know. So this is the product rule of differentiation. Okay. Now, since we are considering a constant pressure process, so the delta P becomes 0 and delta H becomes this equation. So we'll bring this delta E to this side, and this becomes minus P delta V. And we will number this equation as equation number 29. Okay, simple enough. For condensed phases, now since we have this equation, so for condensed phases like solids and liquids, the change in volume doesn't amount to a big quantity. For that reason, since there is not a great amount of change in the amount of volume in solids and liquids, this delta V is almost equal to 0. And therefore, when this, so I'll just write it down. Okay. So for solids and liquids, which are the condensed phases, delta V is almost equal to 0. If that is true, then this quantity is cancelled out, and delta H becomes equal to delta E for solids and liquids for most practical purposes. Okay. Now for gases, this is not true. So what happens when you have a gas? So for gas, now for gases, the same equation holds true. Okay. So we have delta H minus delta E is equal to P del V. Okay, so this is true. Now, if this can be simplified using PV nRT, right? So if it is a ideal gas, we can write this. Now the delta V in here will then, if you use this equation, then P delta V is pressure being constant, this being a constant, so this becomes something like RT delta N for gases. And we will number this equation 30. So for solids and liquids, the change in volume is not a big quantity, it's almost equal to 0. Therefore, this whole term becomes 0, and therefore the enthalpy change is equal to the energy, the internal energy change for solids and liquids, the condensed phases. But for gases, there is a considerable amount of change in volume. So we can also calculate the delta H minus delta E for gases using this equation, that equation number 29. But we can also find out the number, the difference between the enthalpy and the internal energy using this equation. Now the delta N is the difference in the number of moles of gases. So for example, if you have reactants going to products, the total number of moles of gases, say for the left hand sides was 3 mole, and finally the number of moles of gases became 5 mole just for the gases, then delta N in this case becomes 5 minus 3, 2, right? And the same is true for, so whatever the final is, the final minus initial number of moles of gases will supply the number for the delta N. Okay, this is an approximation. Okay, this is not true for all the cases. Now, why is it an approximation? Because in order to get this, we have applied this. So this was the source of the errors, the source of the approximation. Now, why? Because this equation tells that, what are the two approximations? That the gases are ideal. This is the first approximation. And the second is, whenever you are using this for the gases, not only this is just for the gases and the gases being ideal, we are automatically ignoring the delta V, the change in the volumes for the solids and the liquids, if there are any in that reaction. So a reaction can have multiple things in it, right? It might be possible that it's a heterogeneous system. It has both the solids, liquids, and the gases, right? It might have all the three. So whenever we are moving from equation 29 to equation 30, we are getting two assumptions. First, that whatever the gases are, they are behaving ideally. And secondly, whatever the change in the volume for the solids and the liquids are, the delta V is assumed to be 0, okay, which is not always the case. So this is an approximation, okay. So these are the two things that are important when we are trying to understand the difference between delta H and delta E, the internal energies. First, we have to understand what the delta H generally means. So if you are given a reaction and you're asked to find out the change in enthalpy, you will be using this equation. If you know the reaction happening, if you know the HI of the individual reactants and the products, the enthalpy of the individual reactants and the products, and you know the stoichiometric coefficients. Now, if you know that, you can directly calculate the change in enthalpy. Now, if you are asked to find out the change, if the difference between the enthalpy and the energy, the internal energy, you will be using these equations. Okay, so this is the first part. Now, we'll move on to the next part of the course.